It looks like we begin this webinar with a poll. Let's pull it up. Please answer this question. What is the most critical factor in data quality? Click the radio button next to your response, and as soon as everyone has given an answer, we will get the webinar started.
Thanks, Ashley. Obviously, there is no right or wrong answer to our polling question. We have all heard the terms QA and QC. What do these terms mean? In the context of research, a simple definition of quality assurance is a process implemented before data are collected to ensure quality. Quality control, on the other hand, is a process implemented after data are collected to ensure quality. In scientific research, some of the elements of quality assurance should include the research question, an appropriate experimental design, adequate measurement tools, proper installation and usage of the tools, and thorough preliminary testing. The questions to be answered and experimental design are beyond the scope of this webinar, but obviously fundamental to any research. However, we at LI-COR do have quite a lot of experience at soil CO2 flux measurements, and you may want to review some of our application notes and poster papers as you consider your experimental design. One note which may be of interest in this regard is titled Soil CO2 Flux Measurements, Addressing Spatial Variability and Determining the Number of Readings Required. This note is available on our website. As I mentioned, we at LI-COR have quite a lot of experience in soil CO2 flux measurements. This experience is built into the design of the LI-8100 system. See our previous webinars on soil CO2 flux if you would like to hear details on why we believe the LI-8100 system is a great tool for measuring soil CO2 flux. Our manuals give detailed information on installation and usage of the LI-8100. For example, it is important that the soil collar provide a mechanically stable measurement interface between the chamber and the soil. Soil collars are covered in Chapter 2 of the manual. Although weather-tight, the instrument connectors and cases were not designed for submersion. In long-term, unattended measurements at sites which may be exposed to intense precipitation, it is important to keep the instruments up off the soil using bricks, blocks, or even a pallet, as in this example. Direct sunlight can cause overheating of the instruments. Some sort of shading is appropriate under these conditions. The shading could be as simple as foam insulation nailed to the top of 4 stakes pounded into the ground. And when measuring multiple chambers, the potential for air leaks increases. Therefore, it is important to perform a leak test after installing all the chambers in the field to ensure that there are no leaks. The leak test is covered in Chapter 10 of the manual. Preliminary testing of the system is critical. Test to determine the optimum observation length, observation delay, and purge times for your specific conditions. Be sure that the data from the system are reasonable. Do your first quality screening runs on these preliminary data. For unattended measurements, be sure to examine the starting CO2 concentrations carefully. Depending on the site and chamber positioning, a pre-purge time may be needed to be added. Also, if you have attached any ancillary sensors to the system, such as soil temperature or moisture probes, this is the right time to confirm that the data from these probes is reasonable. Quality control is the process we implement after the data are collected to ensure quality. Elements of a quality control program for data from the LI-8100 should include data archiving, checking system setup and constants, checking instrument diagnostics, checking key variables used in the flux calculations, and checking the computed flux values. It should be emphasized at the outset that before any quality control process of data occurs, one should always archive the original data. it would be best to have 2 copies which are archived on separate systems. After archiving, we load a copy of the data into the File Viewer software for analysis. The LI-8100 File Viewer software is a powerful tool. It makes it easy to get an overall summary of an entire season's data from a multi-chamber experiment, and at the same time drill down into the quality and characteristics of an individual observation. In the next few slides, we will walk through the steps you might follow using the File Viewer software to do quality screening of a data set. I have chosen to break down the process into steps which make sense for me. Your process may look different, but it is important to have a strategy before you start the experiment. With experience, this strategy will probably evolve. In my case, I chose to evaluate information by categories: the system constants and setup information, instrument diagnostics, variables used in the flux calculations, and finally, the flux values themselves. It should be emphasized here that just because the final flux values are different from what we expected or what we have experienced in the past, or the variances are large, does not mean we have poor data that should be suspect or worse yet, thrown out. In step 1, we load or open a file or multiple files. This is covered on page 24 of the File Viewer Manual. First, click the Open File button on the toolbar or select the file Open from the main menu. Then use the Open File dialog box to navigate to the desired directory, and select the file to be viewed. Use Ctrl+Click to select an individual file, or by using Shift+Click, you can select multiple files. If multiple files are selected when you click Open, you will be given a choice of combining the files or keeping them separate. In step 2, set up the displayed variables. This is covered on page 11 in the manual. First, click on the Change Variable icon in the toolbar. Choose whether the variable you want is measured or a header variable. We will be doing some of each. If the variable is a measured variable, click the appropriate radio button for the initial value, or mean, or range. In some cases, you may want to display the mean and the range, or the initial value in the range, for the same variable. Click the variables and add them to the included list. When you're done, click OK. Some important diagnostic variables are the bench or erga temperature, the electronics and mux temperatures, system voltage, the multiplexer flow, and time to complete chamber closure. The bench or erga temperature is important because control of the erga temperature minimizes drift and, to some degree, noise in the CO2 signal. The electronics and mux temperatures are important for system reliability and integrity. System voltage can impact system reliability and interruption in operation. Multiplexer flow is critical to the assumptions of good mixing and representative sampling in the flux computations. And finally, complete chamber closure is critical to measurements. The time to close the chamber can be a good indicator of complete closure. In order to pinpoint the sources of problems in the data, we need to have a fundamental grasp of the flux equation and the key variables in the flux calculations. This understanding will help us in investigating the possible failure of a sensor in the system, or a weakness in the experimental protocol, or implementation of the protocol. In the equation, Fc is the soil CO2 flux. V is the system volume, including the chamber, tubing, and erga. P sub 0 is the initial pressure in the chamber. W sub 0 is the initial water vapor mole fraction. R is the gas constant. S is soil surface area. And T sub 0 is the initial air temperature in the measurement chamber. Finally, dC prime dt is the initial rate of change in water-corrected CO2 mole fraction. Key variables that I would suggest screening for from the flux computation include the initial values of atmospheric pressure, air temperature, and dilution-corrected CO2 concentration. Although RH is not directly in the equation, water vapor mole fraction is, but relative humidity may be more useful to screen for because when the relative humidity approaches condensing conditions, there could be concerns about the gas analyzer operation and measurements. Also, remember that RH is a function of water vapor concentration and air temperature, so you should always look at chamber temperature at the same time you are looking at RH. Most of the time, careful screening of the underlying variables will result in a dataset with few, if any, outliers in the calculated flux values. However, it can be instructive to sort the data by the flux values calculated from the linear model and compare these values to the flux computed with the exponential model. The iterations required for convergent solution of the exponential model can also be used for quality flags. In step 3, we set up charts so that you can observe the results of screening outlier data. Briefly, click the Add Chart button. Choose the variable to be charted and the x-axis. And finally, create a chart group so that you can screen multiple variables in one pass. For more details on setting up charts and chart groups, check out page 13 in the manual. After setting up the variables and charts, you can sort observations by a specific field or column of the data. Click the header of the column once to sort maximum to minimum. Click again to sort minimum to maximum. This procedure will allow us to quickly find observations which have variables values which are outliers or just don't make sense. As an illustration, I chose some data from an experiment we conducted in 2007 using 16 chambers. The initial data set contained over 40,000 observations, including what appear to be a number of outliers.
Rick, I'm going to interrupt you with a question. The audience asks, why does the file viewer software compute two flux values, one with an exponential regression and one with a linear regression?
Thanks, Ashley. Let me look for a slide that can address that question. Here we go. To answer that question, let's take a closer look at a single observation, specifically zooming in on the regression analysis. Here we see the water vapor corrected CO2 concentration inside the chamber plotted against time. At time 0, the chamber closes and CO2 begins to increase. It's clear from the data and makes sense physically that the rate of increase in CO2 is greatest when the chamber first closes. If we fit the data with an exponential model as depicted by the red line through the data in this slide, and then solve for the initial slope, we can see that a linear fit of the data, depicted by the black line through the data, underestimates the true flux. In most cases, the exponential fit will be the best estimate of the flux. However, if the data are extremely noisy, or if there are anomalies in the data, it can be difficult to fit it. In fact, here's an example where the data are noisy and the algorithm never converged to fit the exponential model. In this case, we reached 10 iterations without convergence, as you can see in the slide where iterations are circled in red. And the system only reported the linear flux values. While I'm on this slide, I might point out another observation. As you can see, the CO2 concentration before the chamber closed during the negative times was much higher than the CO2 concentration at closure. This occurs occasionally depending upon where the open chamber is set, whether it's over vegetation or some respiring material. You might get very high CO2 concentrations. As you set up your preliminary testing, you should look for this and be sure to add a pre-purge time so that you can get CO2 concentrations down to ambient before the chamber closes. During the screening for instrument diagnostics, we found several records with little or no flow. Without flow, the measured change in CO2 concentration is typically small and may be upward or downward. The regression analysis shown here was from a record with no flow. The stepwise decrease in CO2 concentration leads me to believe that there may have been a flow blockage which caused the low flow. After screening for problems in the fundamental variables, we screened for outliers in the flux values from the linear model. We removed records which had flux values indicating CO2 uptake and 12 records where values were extremely high and may have been due to a rodent inside the chamber. After screening a total of 32 records from the original 40,000 records, I was left with this view. To dig a little deeper into the data and look at more detail, I chose to look at a one-week segment of the data. There appears to be a discontinuity in the data between June 13th and June 14th. However, since I have carefully screened the data using my predetermined process, I can be more confident that the changes I see are real. In fact, there was a 29 millimeter rain on the afternoon of June 13th. This is in conjunction with the fact that some of the soil chambers had significantly more decomposing crop residue, probably explains the variation we observed during this period in the data. One take-home message from this illustration is that if we had thrown out data where there were unexpected on its face difficult to explain changes in flux, we would have lost an opportunity to learn more about the system we were characterizing. Anytime data have more variance than we expected, change in unexpected directions, or have greater magnitudes than we expected, we should look for the underlying cause and not just assume that the data are suspect. Thank you very much for your time. This is the end of my presentation. Ashley, do we have any questions from the audience?
Thanks, Rick. I do have one question for you, and it's, I have relative humidity values that don't make sense. What can I do?
Ashley, that's a tough question, but let me try to address it. Remember, I mentioned earlier that RH or relative humidity, is a function of water vapor concentration and air temperature. It's possible that the relative humidity data don't make sense because your air temperature measurement is, or air temperature sensor is broken. That's the first thing to check. If, in fact, that is the case, what you could possibly do is use air temperature from a different chamber and substitute that into your data set to recompute a relative humidity based on that air temperature. If the relative humidity doesn't make sense because you have liquid water in the system, then unfortunately there's also going to be problems probably in your CO2 data as well. And in that case, you'll probably want to screen the data very carefully to ensure that you don't have CO2 numbers that are also unrealistic. So are there any more questions, Ashley?
I actually don't have any more questions, but it looks like our panelists are still working on some of the questions that were submitted throughout the talk. I'd like to remind our audience that if they'd like to continue their conversation with the panelists or with Rick, they can do so offline or via email. This concludes our replay of quality assurance and quality control of soil CO2 flux datasets. It is also the last webinar in our series of replays. The previous webinars are available from our webinars webpage, www.LI-COR.com/env/webinars. We hope you found this replay series useful. Any questions you have that have not been answered by our live panel can be directed to either Rod or Rick. Their contact information is on the screen as well. Thank you for joining us today. We hope you enjoyed the opportunity to watch a live replay of this event.